A man is riding on a Ferris wheel that's revolving at a constant angular frequency. There's 4 questions. At which point is the net force on the man the greatest and the least? At which point is the force between the man and the Ferris wheel cart that he's riding in the greatest or the least? At which point does the man have the greatest momentum? And at which point does the man have the greatest energy? Pause the video and answer all these questions. The answers are: the net force on the man is the same at all the points. The net force between the man and the cart is the greatest at point E, the bottom, and the least at point A, the top. The momentum of the man is the same at all the points, and the man has the greatest energy at the top, point A. For number 1, net force. Net force is related to the change in momentum versus time. So what's momentum? Momentum is gamma mv. For spinning around in something in a circle, we know the velocity is omega r. And so momentum is gamma m, the mass of the man, omega r. And it's always in the direction of the velocity here. So it's spinning around. In this case, if r is constant, omega is constant, we know that parallel, it's always staying the same magnitude. So in the parallel direction, it's gamma m. If either one of these change, that would change, but we know r and omega are constant, and so therefore there's no change parallel. And so their change here only comes from perpendicular. So this vector is changing direction, so therefore any vector that's changing direction, even if it's changing magnitude, the perpendicular to its motion, so in the direction that it's spinning, there's a term perpendicular to its motion, which is the magnitude of that vector at this time, which is momentum, times the rate at which this directionality is changing, omega. So this is true at all points. It's always pointing inward. So it's perpendicular. It's the magnitude of the momentum, gamma mass of the man, omega r, times omega. So therefore it's gamma m omega squared r. And this is the change of momentum, which is the net force. And since these terms, omega is constant, r is constant, mass of the man is constant, it's a constant, therefore the net force on the man is constant. And also, answering part 3, you can see that the magnitude of the momentum is the same. The magnitude of the momentum is the same at all points. The directionality changes, but the magnitude is the same. If you have problem 2 and we're just asked to understand magnitudes one relative to another, you don't necessarily have to solve all the equations. The fastest way might be to just do things vectorially. And so we need to understand what forces are acting on it and kind of what the net force is. Well, we know that this is going around at a constant angular frequency, and it's at a constant speed and a constant radius, and so therefore the only change of momentum for its time is vectorially inward to the circle, and we've solved for it here. It's this magnitude. So it doesn't matter where he is, the net force is the mass of the man, omega squared r, acting inwardly. So that we know that's the net forces, and thinking about the system being a man, just the man, and everything else acts on him, what forces act on the man from the surrounding? There's a buoyancy force, which we're going to ignore for this case, but that would be constant magnitude. We have gravitational force, which is always mg down, and then we have the force that the cab exerts on the man. Those are the only forces we have acting. So vectorially, you can think about it. At the top, the net force is mass of the man, omega squared r, and it's acting down. At the bottom, it's the exact same magnitude, but it's acting up. On the right side, the net force is the exact same magnitude as these, but it's acting to the left. On the left side, it's the exact same magnitude acting on the right. So I know that all my forces, when added up, have to vectorially add up to be whatever this is. At any point in this, as it goes around, we know one of the forces is mg. So that's down. If there were a buoyancy force, there'd be some little buoyancy force that'd be acting upward. Okay, and that'd also be constant. Okay, so ignoring it for now, so we know that mg is down. And what other force acts on the man? Well, it's the force that the cart pushes on the man. And I know that the net force is this, so that means the sum of all these forces, the mg plus the force in the cab, have to, when added up vectorially, have to become this. And you can see, so I have to add this. What do I have to add to it? I have to add this positive value here. So at the top, so these two forces add up to be the net force. You can see that vectorially, there it is. At the bottom, I know my net force is up, this magnitude. Here's mg. What do I have to add to this to end up with this net force? Well, I add up to something which the delta is that, so it's greater. On the right side, I know my net force is pointing to the left. I have mg. What's the force of the cab of the man that, when added to this one, become that? Well, it has to be this vector in this direction. And on the left side, I know my net force, which is my change of momentum versus time, is this way. There's mg, so my force of the cab on the man has to vectorially be this direction of that magnitude. And then you just look at the problem and say, where is this force the greatest? The force in the cab on the man. Well, it's greatest here. That's at the bottom. So here he'll see the man will feel the greatest force on, and the man will feel the greatest force from the cab, and then the cab would also, the force of the cab on the man is here. The force of the man on the cab would be the opposite of that. So if the cab were to break, it'd break here on the bottom, because that would be the greatest magnitude. Well, where's the force the least between the cab and the man, the magnitude? Well, it's at the top. You can see that right here. And then at any other condition, it's going to be somewhere between those as far as the magnitude, and it'll be vectorially in this, as determined by that individual problem in the orientation. Another thing to see is on the right side and the left side, right at the middle point, these forces have the same magnitude. You know, even though he's going up here and he's going down here, it's not what his velocity or his direction. Because here he's going the same magnitude of velocity he's going there. He's going up and down. What things matter is change in momentum. How is his momentum changing? And you can see that this momentum change is always the same magnitude. So you can, just doing it vectorially, you don't even have to do the numbers. You can right away, you can solve that. If instead the problem, you need to figure out what the value of this green force is, the force of the cab of the man, then you do, well, my net force in my x direction. So in this case, on the top, net force in the x direction, well, there is no forces acting in the x direction, so that's 0. In the y direction, what I'll call positive y, this direction, my net force, from change in momentum, change in time, and in this y direction at the top, well, my net force is downward, so if I call that a positive y, put a coordinate system on here, x and y, here my net force is this, and it's negative. So what are the forces, which is my change of momentum in time in the y direction? My net forces, and that's the sum of all the forces. Well, mg is minus y, so minus mg, and I'll call this plus, and I can solve for this force right here, so it's minus, the force of the cab on the man is minus mass of the man, omega squared r, plus mg. At the bottom, well, I know that again, there's no forces in the x direction. Looking in the y direction, I know my change in momentum dt in the y direction is my net force, which is this. So that's positive y, so positive here equals, and now I'll put all my forces. I got a minus mg, that's in the minus y direction, we'll call plus force of the cab on the man, and I can solve for it, and so there's its magnitude. At point C there, which is at the y direction, and if I again draw my free diagram of the man, I know at this moment in time my dt dt only has a minus x term, if I call this x and y. And there is no net dp dt at this moment in the y direction. So my net force only acts in this direction. So if I think about the x direction here, which is right here, I call this a positive x, I may know my dp dt in the x direction, which is my net force, in the x direction is a minus, because it's acting this way, mass omega squared r, and mg doesn't have any x component, so the only thing I have is my force in the cab in the x direction, so I can see my force in my cab in my x direction is this term right here, which you can kind of see from the vectorial part right here, is force, and then in the y direction, my dp dt in the y direction is 0, so therefore my net force in the y direction is 0. So parallel dp, since it's not constant radius and I don't have a change in omega versus time, then that's 0. So in the y direction all I have is my minus mg, that's in the minus y direction, plus some force of the cab on the man in the y direction, so I can solve for that, and that's mg. So now I have my components in the y direction, it's mg, this force. In the x direction, it's minus m omega squared r. X and y are vectorially 90 degrees from each other, so Pythagorean's rule, here I could solve for the magnitude of the force on the cab, if I wanted to know it exactly. And then just the kind of the opposite case happens when I'm on the left side. You can see that vectorially it's going to be the exact same magnitude as this. It'll just be in a different vectorial direction. With regard to the total energy of the man at any point, energy has many forms. Rest energy, mc squared. Assume the mass of the man is the same at all points, so that's the same. The sum of rest energy and translational kinetic energy is gamma mc squared, so that's another way to think about it. Or translational kinetic energy is on the Earth 1/2 mv squared. We're going to say the magnitude of the velocity is the same at all points, so that's going to be constant. Another way to think about it, if you were approaching the speed of light in a vacuum, the more correct would be gamma minus 1 mc squared, translational kinetic energy, or p squared over gamma plus 1 over m. Rotational kinetic energy is 1/2 moment of inertia of the man about his own center times omega squared. Rotation of the man about his own center. The man is actually not even rotating about his own center. If the man were spinning, so if he were strapped to it and he was facing this way and this way, he would have some of that, and omega would be the same frequency as this Ferris wheel, but he's actually just always facing upwards, so that's actually 0. But in either case, it'd be the same, either 0, but if he was strapped and turning, there'd be some value here to his rotational kinetic energy, but it would be the same at all points. Some path-independent potential energies, gravitational potential energy, two forms which also are identical in results. So the more general one, minus g m1 m2 over r, going like this. So as r gets greater and greater, it's moving farther and farther away. So this higher up is up here, lower down is down here. So as he gets farther away, the potential energy increases. At the surface of the Earth, this change right here, surface of the Earth, convenient to do MGH, which we'll use. Either one of these cases, you'll see that the farther the person gets from the center of the Earth, or H would be the surface of the Earth. That's a very convenient form to use. The higher up he gets, rather, the surface of the Earth, more potential energy. So A has more potential energy here than E, so A would be the greatest. Electric potential energy, either plus or minus, depending on whether The two things that are, they're attracting or they're repelling. If they're both minuses, then they're repelling. If one was a plus and one is a minus, it'd be attracting. Q1, Q2 over 4 pi E over R. There is none of this acting for this man. As an entire free body diagram, multiple atom system. So no change here. Spring potential energy, 1/2 K S squared. There's no springs acting, so nothing here. Internal energy, just thinking not about magnitude, but actually changes in it. So change in internal energy would be a specific heat times the mass of the man times delta T, where this would be the temperature, not time. We'll assume the man's constant temperature, same temperature at all different places, so therefore his internal energy relative to temperature is the same. So the only one that's any different is gravitational potential energy. Therefore, he has the most energy at A and the least at E.